context. Luckily, I found it. That Rosetta Stone is a book called Secrets of Cold War Technology, Project HARP and Beyond, written by Jerry Vassilatos. In Chapter 1, titled Nikola Tesla and Radiant Energy, Jerry recounts those heady days back in 1890, when Nikola Tesla is developing the experiments which lead to the invention of Tesla's magnifying transmitter. For those of you who have not seen this book before, I highly recommend that you acquire and read the entire book. It is an astonishing work, currently available from Adventures Unlimited Press. But for the purposes of tonight's thesis, I would like to read for you selected sections from Chapter 1, which will lay the foundation for you to completely comprehend Tesla's amazing magnifying transmitter, as well as Gray's cold electricity circuit. My recital begins on page 25 of Secrets of Cold War Technology by Jerry Vassilatos. James Clerk Maxwell predicted the possibility that electromagnetic waves might exist. In theoretical discussions designed to more thoroughly explain his mathematical descriptions, Maxwell asked his readers to consider two different kinds of electrical disturbance possibly existing in nature. The first consideration dealt with longitudinal electric waves, a phenomena which required alternating concentrations of electrostatic field lines. This densified and rarefied pulsation of electrostatic fields necessarily demanded a unidirectional field, one whose vector was fixed in a single direction. The only variable permitted in generating longitudinal waves was the concentration of the field. Subsequent propagation along the electrostatic field lines would produce pulsating thrusts of charge, pulsations moving in a single direction. These electrical sound waves were rejected by Maxwell, who concluded that such a condition was impossible to achieve. His second consideration dealt with the existence of transverse electromagnetic waves. These required the rapid alternation of electrical fields along a fixed axis. Space-spreading electrical lines would supposedly bend to and fro under their own momentum, while radiating away at the speed of light from the alternating source. Corresponding forces, exact duplicates of the alternations produced at the source, would be detected at great distances. He encouraged the experimenters to seek this waveform, suggesting possible means for achieving the objective. And so the quest to find electromagnetic waves began. In 1887, Heinrich Hertz announced that he had discovered electromagnetic waves, an achievement at that time of no small import. In 1889, Nikola Tesla attempted the reproduction of Hertz's experiments. Conducted with absolute exactness in his elegant South Fifth Avenue laboratory, Tesla found himself incapable of producing the reported effects. No means, however applied, would produce the effects which Hertz claimed. Tesla began experimenting with abrupt and powerful electric discharges, using capacitors charged to very high potentials. He found it possible to explode thin wires with these abrupt discharges. Dimly perceiving something of importance in these experiments, Tesla abandoned these experiments, all the while pondering the mystery and suspecting that Hertz had somehow mistakenly associated electrostatic inductions or electrified shock waves in air for true electromagnetic waves. In fact, Tesla visited Hertz and personally proved these refined observations to Hertz, who, being convinced that Tesla was correct, was about to withdraw his thesis. Hertz was truly disappointed, and Tesla greatly regretted having to go to such great lengths with such an esteemed academician in order to prove his point. But while endeavoring toward his own means for identifying electrical waves, Tesla was blessed with an accidental observation which forever changed the course of his experimental investigations. In his own attempts to achieve where he felt Hertz had failed, Tesla developed a powerful method by which he hoped to generate and detect real electromagnetic waves. Part of this apparatus required the implementation of a very powerful capacitor bank. This capacitor battery, as he called it, was charged to a very high voltage and subsequently discharged through short copper bus bars. The explosive bursts thus obtained produced several phenomena which deeply impressed Tesla, far exceeding the power of any electrical display he had ever seen. These proved to hold an essential secret which he was determined to uncover. The abrupt sparks, which he termed disruptive discharges, were found capable of exploding wires into vapor. They propelled very sharp shock waves, which struck him with great force across the whole front of his body. They propelled very sharp shock waves, which struck with extreme force. Of this surprising physical effect, Tesla was exceedingly intrigued. Rather more like shotguns of extraordinary power than electrical sparks, Tesla was completely absorbed in this new study. These electrical impulses produced effects commonly associated only with lightning. The explosive effects reminded him of similar occurrences observed with high-voltage DC generators. A familiar experience among workers and engineers, the simple closing of a switch on a high-voltage dynamo often brought a stinging shock, the assumed result of a residual static charging. This hazardous condition only occurred with the sudden application of high-voltage DC. This crown of deadly static charge stood straight out from highly electrified conductors, often seeking ground paths which included workmen and switchboard operators. In long cables, this instantaneous charge effect produced a hedge of bluish needles, pointing straight away from the line into the surrounding space. The hazardous condition appeared briefly at the very instant of switch closure. The bluish sparking crown vanished a few milliseconds later, along with the life of any unfortunate who happened to be so struck. After the brief effect passed, the systems behaved as designed. Such phenomena vanished as charges slowly saturated the lines and systems. After this brief surge, current flowed smoothly and evenly as designed. The effect was a nuisance in small systems, but in large regional power systems where voltages were excessive, it proved deadly. Men were killed by the effect, which spread its deadly electrostatic crown of sparks throughout the component systems. Though generators were rated at a few thousand volts, such mysterious surges represented hundreds of thousands, even millions of volts. The problem was eliminated through the use of highly insulated, heavily grounded relay switches. Former engineering studies considered only those features of power systems which accommodated the steady-state supply and consumed power. It seemed as though larger systems required both surge and normal operative design considerations. Accommodating the dangerous initial supercharge was a new feature. This engineering study became the prime focus of power companies for years afterwards, safety devices and surge protectors being the subject of many patents and texts. Tesla knew that the strange supercharging effect was only observed at the very instant in which dynamos were applied to the wire lines, just as in his explosive capacitor discharge. Though the two instances were completely different, they both produced the very same effects. The instantaneous surge supplied by dynamos briefly appeared super-concentrated in the long lines. Tesla calculated that this electrostatic concentration was several orders of magnitude greater than any voltage which the dynamo could supply. The actual supply was somehow being amplified or transformed. But how? The general consensus among engineers was that this was an electrostatic choking effect. Many concluded that it to be a bunching action where powerfully applied force was unable to move charge quickly through a system. Mysterious, the combined resistance of such systems seemed to influence the charge carriers before they were able to move away from the dynamo terminals. Like slapping water with a rapid hand, the surface seemed solid. So it was with the electrical force, charges meeting up against a seemingly solid wall. But the effect lasted only as long as the impact. Until current carriers had actually caught up with the applied electrostatic field, the charges sprang from the line in all directions. A brief supercharging effect could be expected until charges were distributed, smoothly flowing through the whole line and system. The dynamo itself thus became the brief scene of a minor shock wave. He began wondering why it was possible for electrostatic fields to move more quickly than the actual charges themselves, a perplexing mystery. Was the field itself an entity which simply drove the more massive charges along? If this was true, then of what was the electrostatic field itself composed? Was it a field of smaller particles? The questions were wonderfully endless. Despite the wonderful ideas which this study stimulated, Tesla saw a practical application which had never occurred to him before. Consideration of the dynamo supercharging effect suggested a new experimental apparatus. It was one which could greatly outperform his capacitor battery in the search to find true electrical waves. A simple high-voltage DC generator provided this electrical field source. Tesla understood that the resistance of the lines, or components, viewed from the dynamo end, seemed to be an impossible barrier for charge carriers to penetrate. This barrier caused the bunching effect. Electrostatic charges were literally stopped and held for an instant by the line resistance, a barrier which only existed during the brief millisecond interval in which the power switch was closed. The sudden force application against this virtual barrier squeezed charge into a density impossible to obtain with ordinary capacitors. It was the brief application of power, the impact of charge against the resistance barrier, which brought it this abnormal electrodensified condition. This is why the conductive wires in his present experiment often exploded. The analogy to steam power and steam engines was unmistakable. Large steam engines had to be valved very carefully. This required the expertise of old and well-experienced operators who knew how to open up an engine without rupturing the vessels and causing a deadly explosion. Too suddenly valved, and even a large steam engine of very high capacity could explode. Steam also had to be admitted into a system gently until it began smoothly and gradually flowing into every orifice, conduit, and component. Here, too, was the mysterious choking effect, where a large capacity system seemed to behave like an uncommonly high resistance to any sudden and sustained application of force. The academic world of experimenters was yet fixated on his former discovery of high-frequency alternating currents. It seemed that Tesla alone now exclusively studied these impulse discharges. He was producing explosive impulses which had not been observed in laboratories. Every component was carefully insulated, himself implementing insulated rods and rubberized regalia to ensure complete safety. Tesla had observed electrostatic machines whose ability to charge insulated metals was potent. But this demonstration exceeded the mere charging of wires by the instantaneous switch closure. This effect produced springing charge, phenomena like no other before witnessed by Tesla for its sheer strength. Whatever the conditions observed in previous systems, he had now learned how to maximize the effect. Balancing voltage and resistance against capacity, Tesla learned to routinely produce supercharged states which no existing device could equal. Empirical observation had long taught that ordinary capacitor discharges were oscillating currents, spark currents which literally bounced back and forth between the capacitor plates until their stored energy was wasted away. The high voltage of the dynamo exerted such an intense unidirectional pressure on the densified charges that alternations were impossible. The only possible backrushes were oscillations. In this case, charges surged and stopped in a long series until the supercharge was wasted away. All parameters which forced such oscillations actually limited the supercharge from manifesting its total energetic supply, a condition which Tesla strove to eliminate. Indeed, he spent an excessive time developing various means to block every backrush and other complex current echo which might force the supercharge to prematurely waste its dense energy. Here was an effect demanding a single unidirectional superpulse. With both the oscillations and alternations eliminated, new and strange effects began making their appearance. These powerful and penetrating phenomena were never observed when working with high-frequency alternations. The sudden, quick closure of the switch now brought a penetrating shock wave throughout the laboratory, one which could be felt both as a sharp pressure and a penetrating electrical irritation, a sting. Face and hands were especially sensitive to the explosive shock waves, which also produced a curious stinging effect at close range. Tesla believed that material particles approaching the vapor state were literally thrust out of the wires in all directions. In order to better study these effects, he poised himself behind a glass shield and resumed the study. Despite the shield, both shock waves and stinging effects were felt by the now mystified Tesla. This anomaly provoked a curiosity of the very deepest kind, for such a thing was never observed before. More powerful and penetrating than the mere electrostatic charging of metals, this phenomena literally propelled high-voltage charge out into the surrounding space, where it was felt as a stinging sensation, the stings lasting for a small fraction of a second, the instant of switch closure. But Tesla believed that these strange effects were a simple effect of ionized shock waves in air, rather like a strong ionized thunderclap. Tesla devised a new series of experiments to measure the shock wave pressure from a greater distance. He required an automatic trip switch. With this properly arranged, a more controlled and repetitious triggering of the effect was possible. In addition, this arrangement permitted distant observations which might cast more light on the shield penetrating phenomenon. Controlling the speed of the high-voltage dynamo controlled the voltage. With these components properly adjusted, Tesla was able to walk around his large gallery spaces and make observations. Wishing also to avoid the continuous pressure barrage of its stinging sparks, Tesla shielded himself with several materials. The arrangement of rapidly interrupted high-voltage direct currents resulted in the radiation of stinging rays, which could be felt at great distances from their super-sparking source. In fact, Tesla felt the stings right through the shields. Whatever had been released from the wires during the instant of switch closure successfully penetrated the shields of glass and of copper. It made no difference. The effect permeated each substance as if the shield were not there at all. Here was an electrical effect which communicated directly through the space without material connections. Radiant electricity. In these several new observations, the phenomena was violating electrostatic charge principles experimentally established by Faraday. Projected electrostatic charges normally spread out over the surface of metallic shields. They do not penetrate metal. This effect had certain very non-electrical characteristics. Tesla was truly mystified by this strange new phenomena and searched the literature for references to its characteristics. In one case, Joseph Henry observed the magnetization of steel needles by a heavy spark discharge. The extraordinary feature of this observation in 1842 lay in the fact that the Leyden jar, whose spark apparently produced the magnetizations, stood on the upper floor of an otherwise electrically impervious building. Brick walls, thick oak doors, heavy stone floors, iron ceilings. Moreover, the steel needles were housed in a vault in the cellar. How did the spark affect such a change through such a natural barrier? Dr. Henry believed that the spark had released special light-like rays, and that these were the penetrating agencies responsible for the magnetizations. A second such account in 1872 occurred in a high school building in Philadelphia. Elihu Thomson, a physicist instructor, sought to make the sparks of a large Ruhmkorff spark coil more visible for his next lecture. Attaching one pole of the coil to a cold water pipe, he reactivated the coil. Thomson was thrilled to find that the nature of the spark had changed from blue to white. Wishing to amplify this effect, Thomson attached the other pole to a large metal tabletop. Again, reactivating the coil produced a shrieking silver-white spark, entirely visible to anyone who sat in the last row. Wishing to show this to a colleague, Edwin Houston, Thomson made for the door and was abruptly stopped. Touching the brass knob on the otherwise insulated oak door, Thomson received an unexpected sizzling shock. Turning off the Ruhmkorff coil, Thomson found it was possible to stop the effect. Calling for Edwin, he summarized what had occurred, then turned the unit back on. The stinging charge effects returned. The two gentlemen ran around the huge stone, oak, and iron building with insulated metal objects now. Each touch of a penknife or a screwdriver to anything metallic, however distant from the coil or insulated from the floor, produced long and continuous white sparks. The account was written up as a short article in Scientific American later in the same year. In studying each of these two prior observations, events which were separated by some 30 years, Tesla perceived an essential unity with that of his own discovery. Each observation was perhaps a slight variant of the very same phenomenon. Somehow, accidentally, each experimenter had managed to produce the explosive supercharging effect. In the case of Dr. Henry, the explosive bursts occurred in a single flash, electrostatic machines being used to accumulate the initial charge. The second case was peculiar, since it evidenced the sustained and continuous production of supercharging effects. The effect was rare because it obviously required very stringent electrical parameters. Tesla deduced this from the simple fact that the effect was so infrequently observed by experimenters all over the world. In addition, he was quick to remark concerning the anomalous attributes attached to the phenomenon. Tesla knew that despite the extremely penetrating effects in each case, he had secured the only means for achieving the complete and maximum manifestation of supercharging. This was an apparatus with no equal, capable of releasing an aspect of the electrostatic field which others had very apparently not had. Though discovered by Tesla in 1889, the preliminary observation of this effect was published after an intense battery of investigations. The Dissipation of Electricity, published just prior to Christmas of 1892, is the pivotal Tesla lecture. This is the departure point in which Tesla abandons research and development of high-frequency alternating current. Divorcing himself from the field entirely, Tesla describes the shock waves and other effects of impulses. In addition to those physical sensations which he describes in characteristic understatements, Tesla also enlarges upon the gaseous aspects associated with the phenomenon. He observed that the abruptly charged wires in his experiments projected a strange gaseous stream when immersed in an oil bath, a phenomena which he once thought due entirely to wire-adsorbed gases. He found that the effect could be so continuously produced from a single wire that no amount of ordinary adsorbed gas could possibly supply the flow. Indeed, he was able to produce streams of this kind in oil which so powerfully projected from the charged wire ends that they visibly depressed the oil into a hole, sometimes 2 inches in depth. Tesla began to realize the true nature of this fine issuing gas, which projected from wire ends immersed in oil. He now prepared an extensive series of tests in order to determine the true cause and nature of these shocking air pulses. In his article, Tesla describes the shield permeating shocks as sound waves of electrified air. Nevertheless, he makes a remarkable statement concerning the sound, heat, light, pressure, and shock which he sensed passing directly through copper plates. Okay. Collectively, they imply the presence of a medium of gaseous structure, that is, one consisting of independent carriers capable of free motion. Since air was obviously not this medium, to what was he referring? Further in the article, he clearly states that besides the air, another medium is present. Through successive experimental arrangements, Tesla discovered several facts concerning the production of this effect. First, the cause was undoubtedly found in the abruptness of charging. It was in the switch closure, the very instant of closure and break, which thrust the effect out into space. The effect time. Second, found no reversal of current was permissible, else the effect would not manifest. In this, Tesla made succinct remarks describing the role of capacity in the spark radiative circuit. He found that the effect was powerfully strengthened when placing a capacitor between the disruptor and the dynamo. While providing a tremendous power to the effect, the dielectric of the capacitor also served to protect the dynamo windings. The effect could also be greatly intensified to new and more powerful levels by raising the voltage, quickening the switch make-break rate, and shortening the actual time of switch closure. Thus far, Tesla employed rotating contact switches to produce his unidirectional impulses. When these mechanical impulse systems failed to achieve the greatest possible effects, Tesla sought a more automatic and powerful means. He found this automatic switch in several electrical arc dischargers. The high voltage output of a DC generator was applied to twin conductors through his new arc mechanism, a very powerful permanent magnet sitting crosswise to a discharge path. The discharge arc was automatically and continually blown out by this magnetic field. Imperative toward obtaining the desired rare effect, the capacitor and its connected wire lines had to be so chosen as to receive and discharge the acquired electrostatic charge in a unidirectional staccato fashion. The true Tesla circuit very much resembles a pulse jet, where no back pressure ever stops the onrushing flow. Electrostatic charge rises to a maximum and is discharged much more quickly. The constant application of high voltage dynamo pressure to the circuit ensures that the continual successions of charge, rapid discharge, are obtained. It is then and only then that the Tesla effect is observed. Pulses literally flow through the apparatus from the dynamo. The capacitor, disruptor, and its attached wire lines behave as a flutter valve. The high voltage dynamo remains the true electrostatic source in the apparatus. This is a fact well appreciated by Tesla, who disliked the painful radiant effects proceeding into space. It was evident that the dynamo had somehow been modified by the addition of these pulsing valve circuits. The dynamos being used provided deadly voltages capable of killing a man. The valve circuits were forcing a strange radiance of those deadly field energies. Somehow, the dynamo energy was being expanded into space with dangerous and painful force. But how? By what mysterious and provocative means was this condition established? The result of this experimental series fixed a new concept in Tesla's mind. Tesla had, of course, realized the implications of this mysterious shocking field effect. This was radiant electricity. Tesla first conducted elaborate and extensive investigations in order to comprehend the exact nature of this new electrical effect. Tesla realized that this strange shocking field actually radiated through space from the impulse apparatus. If this was electrostatic energy, it was more intense and more penetrating than any electrostatic field he had ever observed. If this was merely a shuttered electrostatic field, why then was its strength so very intensified? Tesla began to believe that he had discovered a new electrical force, not simply a treatment of an existing force. It is for this reason that he often described the effect as electrodynamic or more electrostatic. By properly adjusting the inherent circuit parameters, Tesla learned how to produce an extremely rapid series of unidirectional impulses on demand. When the impulses were short, abrupt, and precise in their successions, Tesla found that the shocking effect could permeate very large volumes of space with apparently no loss of intensity. He also found that the shocking effect penetrated sizable metal shields and most insulators with ease. Developing a means for controlling the number of impulses per second, as well as the intermittent time intervals between each successive impulse, he began discovering a new realm of effects. Each impulse duration gave its own peculiar effects. Able to feel the stinging shocks, though shielded at a distance of nearly 50 feet from his apparatus, Tesla recognized at once that a new potential for electrical power transmission had been revealed to him. Tesla was first to understand that electrical shock waves represented a new means for transforming the world, even as his polyphase system had already done. Tesla fully intended to disclose his discoveries to the world at large. Radiant electricity had special characteristics of which the scientific world had no knowledge. Working with a simple but powerful embodiment of his original apparatus, Tesla found that radiant electricity could induce powerful electrical effects at a distance. These effects were not alternations, not alternating waves. They were longitudinal waves, composed of successive shocking waves. The advance of each shocking wave, followed by short neutral zones, together comprised the radiant field. Vectorial components of these shock wave successions were always unidirectional. The shuddering shock waves were capable of forcing charge in the direction of their propagation. Objects placed near this device became powerfully electrified, retaining a single charge sign for many minutes after the magnetic disruptor had been deactivated. Tesla found it possible to amplify these single charge effects by a simple asymmetrical alignment of the magnetic disruptor. By placing the magnetic disruptor closer to one or the other side of the charging dynamo, either force positive or force negative vectors could be selected and projected. Thus, charge could be projected into or drawn from any object in the field space. This was a new electrical force. Tesla realized more than ever that he was in unknown territory. The fact that these radiant forces traveled as light-like rays distinguished them from the electromagnetic waves of Maxwell. Tesla wished to determine the effect of gradually decreasing impulse durations, a job that required the greatest skill and precaution. Tesla knew that he would be exposing himself to mortal danger. Controlling the rapidity of current blowout in the magnetic DC arc, Tesla released a new spectrum of light-like energies throughout his large gallery space. These energetic species were like no other which the world has ever seen since. Tesla found that the impulse duration alone defined the effect of each distinct spectrum. These effects were completely distinctive, endowed with strange additional qualities never purely experienced in nature. Trains of impulses, each exceeding 0.1 milliseconds in duration, produced pain and mechanical pressure. In this radiant field, objects visibly vibrated and even moved as the force field drove them along. Thin wires exploded into sudden bursts of the radiant field. Pain and physical movement ceased when impulses of 100 microseconds or less were produced. With impulses of 1 microsecond duration, strong physiological heating was sensed. Further decreases in impulse duration brought spontaneous illuminations capable of filling rooms and vacuum globes with white light. At these impulse frequencies, Tesla was able to stimulate the appearance of effects which are normally admixed among the electromagnetic energies inherent in sunlight. Shorter impulses produced cool, room-penetrating breezes with an accompanying uplift in mood and awareness. There were no limits in this progression towards impulses of diminished duration. None of these impulse energies could be duplicated through the use of high-frequency harmonic alternations. Few could produce these effects because so few understood the absolute necessity of observing those parameters set by Tesla. These facts have been elucidated by Eric Dollard, who also successfully obtained the strange and distinct effects claimed by Tesla. By 1890, after a period of intense experimentation and design development, Tesla summarized the components necessary for the practical deployment of a radiant electrical power distribution system. Tesla had already discovered the wonderful fact that impulse durations of 100 microseconds or less could not be sensed and would do no physical harm. He planned to use these in his power broadcasts. Furthermore, Shocking waves of 100 microsecond duration passed through all matter, a fitting form of electrical energy to broadcast through a power-hungry city. Tesla made a most startling discovery the same year, when he placed a long, single-turn copper helix near his magnetic disruptor. The coil, some 2 feet in length, did not behave as did solid copper pipes and other objects. The thin-walled coil became ensheathed in an envelope of white sparks. Undulating from the crown of this coil were very long and fluidic silver-white streamers, soft discharges which appeared to have been considerably raised in voltage. These effects were greatly intensified when the helical coil was placed within the disruptor wire circle. Inside this shock zone, the helical coil was surrounded in a blast which hugged onto its surface and rode up the coil up to its upper end. It seemed as though the shock wave actually pulled away from surrounding space to cling to the coil surface, a strange, attractive preference. The shock wave flowed over the coil at right angles to the windings, an unbelievable effect. The sheer length of the discharges leaping from the helix crown was incomprehensible. With the disruptor discharge jumping 1 inch in its magnetic housing, the white flimmering discharges rose from the helix to a measured length of over 2 feet. This discharge equaled the very length of the coil itself. It was an unexpected and unheard of transformation. Here was an action more nearly electrostatic in nature, although he knew that academes would not comprehend this term when used in this situation. Electrostatic energy did not fluctuate, as did his shock waves. The explosive shock wave had characteristics unlike any other electrical machine in existence. Yet Tesla stated that the shock wave, during the brief instant in which it made its explosive appearance, more nearly resembled an electrostatic field than any other known electrical manifestation. Just as in electrostatic friction machines, where current and magnetism are negligible, a very energetic field component fills space in radiating lines. This dielectric field normally launches through space in a slow growth as charges are gathered. Here was a case where a DC generator provided the high voltage. This voltage charged an insulated hoop of copper, growing to its maximum value. If all values in the circuit were properly balanced, in the manner prescribed by Tesla, a sudden charge collapse would then occur. This collapse was necessarily very much shorter than the interval required to charge the loop. The collapse comes when the magnetic disruptor extinguishes the arc. If the circuit is properly structured, no backrush alternations ever occur. This unidirectional succession of charge-discharge impulses causes a very strange field to expand outward, one which vaguely resembles a shuddering or staccato electrostatic field. But these terms did not satisfactorily describe the conditions actually measured around the apparatus, a powerful radiant effect exceeding all expectable electrostatic values. Actual calculation of these discharge ratios proved impossible. Implementing the standard magneto-inductive transformer rule, Tesla was unable to account for the enormous voltage multiplication effects. Conventional relationships failing, Tesla hypothesized that the effect was due entirely to radiant transformation rules, obviously requiring empirical determination. Subsequent measurements of discharge lengths and helix attributes provided the necessary new mathematical relationships. He had discovered a new induction law, one where radiant shock waves actually auto-intensified when encountering segmented objects. The segmentation was the key to releasing the action. Radiant shock waves encountered a helix and flashed over the outer skin from end to end. this shock wave did not pass through the windings of the coil at all, treating the coil surface as an aerodynamic plane. A consistent increase in electrical pressure was measured along the coil surface. Indeed, Tesla stated that voltages could often be increased at an amazing 10,000 volts per inch of axial coil surface. This meant that a 24-inch coil could absorb radiant shock waves which initially measured 10,000 volts, with a subsequent maximum rise to 240,000 volts. Such transformations of voltage were unheard of with apparatus of this volume and simplicity. Tesla further discovered that the output voltages were mathematically related to the resistance of the turns in the helix. High resistance meant higher voltage maxima. He began referring to his disruptor line as his special primary, and to the helical coil placed within the shock zone as his special secondary. But he never intended anyone to equate these terms with those referring to magnetoelectric transformers. This discovery was indeed completely different from magnetoinduction. There was a real and measurable reason why he could make this outlandish statement. There was an attribute which completely baffled Tesla for a time. Tesla measured a zero current condition in these long copper secondary coils. He determined that the current which should have appeared was completely absent. Pure voltage was rising with each inch of the coil surface. Tesla consistently referred to his electrostatic induction laws, a principle which few comprehended. Tesla called the combined disruptor and secondary helix a transformer. Tesla transformers are not electromagnetic devices. They use radiant shock waves and produce pure voltage without current. Each transformer conducted a specific impulse duration with specific force. Therefore, each had to be tuned by adjusting the disruptor to that specific impulse duration. Adjusting the arc distance provided this control factor. Once each transformer was tuned to its own special response rate, impulses could flow smoothly through the system, like gas flowing through a pipe. Finding the gas dynamic analogies and applications indeed provided him with a consistent record of successful assessments of these regards. Tesla began considering whether or not the white flame discharges, so different from anything that he had ever seen, might not be a gaseous manifestation of electrostatic force. There were certainly abundant experimental instances in which a purely gaseous nature, so unlike anything electrical, was being clearly made manifest. The manner in which the radiant shock wave traveled over the wire coilings in white flimmering laminar sheets brought a new revelation of thought. Voltage pulses traversed the secondary surface like a gas pulse under increasing constriction. Until reaching the free end of the coil, these gaseous pulses flowed over the copper surface rather than through it. Tesla referred to this specific manifestation as the skin effect. In this, the discharge greatly resembles the manner in which gases move over surfaces aerodynamically. Furthermore, whenever a metal point was connected to the upper terminal of one of his transformers, the stream became more directive. It behaved just like a stream of water in a pipe. When the white flimmering stream was directed at distant metal plates, it produced electronic charges. This charge production could be measured as amperage, current at the reception site. In transit, however, no such amperage existed. Amperage appeared only when intercepted. Eric Dollard has stated that the space surrounding Tesla impulse transformers so surge with these streams that the interception currents can reach several hundred or even several thousand amperes. But what was this mysterious stream composed? Tesla struggled with the doubt that these discharge phenomena might be ordinary electricity behaving in extraordinary ways. But did electricity indeed have a smooth, soft, and flimmering nature? The electricity with which he was familiar was shocking, hot, burning, deadly, piercing, stinging, all the attributes of an irritant. But this discharge phenomena, whether cool or warm to the touch, was soft and gentle, and it would not kill. Even the manner in which the pulse exploded as bright white discharges of greatly transformed voltage suggested the way in which gases behave when released from their confinements under pressure. These reflective meditations convinced Tesla that this effect was not purely electrical in nature. Closely examining the white flames, Tesla realized why there was no measurable electric current in the crown of these activated coils. The normal heavy charge carriers, electrons, could not travel as quickly as the radiant pulse itself. Choked in the metallic lattice of the coil, electrons became immobile. The radiant pulse which moved over the coil's surface was therefore not electronic in nature. Additionally, Tesla discovered an amazing phenomena which removed all doubt concerning the true nature of the energetic carriers at work in his apparatus. Tesla arranged a very heavy U-shaped copper bus bar, connecting both legs directly to his disruptor primary. Across the legs of this U-shaped bus bar were placed several incandescent lamps. The arrangement was a very evident short circuit. The lamps were illuminated to a bright, cold, white light, while being shorted by a heavy copper shunt. Uncharacteristic of particulate current electricity, the bright but cold lamps revealed that another energetic current was indeed flowing through the short circuits. Those who observed this experiment did not expect it to perform any function save the incineration of the disruptor circuit and possibly of the dynamo itself. Instead of this, witnesses beheld a marvel. The lamps lit to an uncommon brightness. In this simple demonstration, Tesla was illustrating but one of his many evidences. Electronic charges would prefer the least resistant circuit, rejecting the incandescent bulbs for the copper path. The circuit in this situation chose to conform to a contradictory principle. Perhaps this was true because the current were not electrical. Tesla repeatedly used this demonstration to evidence the fractionation of currents electronic from currents neutral. A single question remained, the answer to which would provide him with the essential information needed to create a new technology. What so separated or fractioned the diverse mobile carriers in his transformer? It was the geometric configuration of the coil, which inadvertently separated each component. Electrons were blocked from flowing through the wire length, while the radiant pulse was released over the coil's surface as a gaseous pulse. Electrons could not drift through the wire, but during each impulse period, they were blocked by the line resistance. Thus, the gaseous mobile carriers were released to flow outside the wire, a pulse which traveled along the outer coil surface from end to end. Here then was evidence that electrical discharges were indeed composed of several simultaneous mobile species. Tesla now comprehended why his first high-frequency alternating currents never evidenced these powerful actions. It was the abruptness, the violence of the impulsive discharge which gave free mobility to this unsuspected gaseous component. Impulses, unidirectional impulses, were the only means by which these potentials could be unlocked. Alternations were absolutely useless in this regard. Moreover, because alternations could not unleash the secondary gas dynamic component, it remained an unusable and pitifully weak means. Tesla forever viewed his high-frequency alternating devices as failed projects. This has great bearing on his highly critical views of Marconi and all others like him who pursued high-frequency alternating wave radio. Tesla began to study a topic which has found more enemies and critics than any this century. Tesla, with great interest now, began researching the ether. Tesla came to believe that dielectric fields were actually composed of ether streams. Theoretically, then, one could derive limitless energy by trapping and conducting a naturally occurring dielectric field line. The problem was that no ordinarily accessible material could resist the ether enough to derive any momentum from it. With a stream so rare as to pass through all known materials, the kinetic energy inherent in dielectric field lines would remain an elusive energy source. Tesla believed he may have found the secret to tapping this energy, but it would not require an ordinary kind of matter. Tesla viewed voltage as streams of ether under various states of pressure. Raising these stresses could produce enormous ether streams, where the observed voltage would then be extremely high and luminous. This was the very condition which Tesla had come to believe had been established in his transformers. In fact, Tesla repeatedly stated that his transformers affected powerful movements in the ether. In one truly mystifying experiment, indicative of these comprehensions, Tesla describes the production of very rapid impulse trains with the subsequent production of a cool, misty white streamers extending a yard into space. These were cool to the touch and harmless. If electrical in nature, they would necessarily have been several million volts in potential. Their harmlessness is coupled with their sinuous nature, one completely unlike electrical currents. Indeed, to understand Tesla technology, one must eliminate the notion that electrons are the working fluid in his radiant electric systems. With the lower coil end connected directly to the dynamo, high-voltage ether streams were projected from the upper terminal. When describing each of his relevant patents in this new technology, Tesla forever spoke of light-like rays and the natural medium. The first term refers to the tightly constricted ether streams, which are propelled from his transformers along infinitesimal ray lines, and the latter refers to the all-pervading ether atmosphere in which his technology operated. It is impossible to comprehend Teslian technology apart from the controversial topic concerning the ether. Many analysts will reject the concept without first seeking out and discovering the proofs which have been established by experimenters such as Eric Dollard. Tesla addressed the notion that ether streams were being pulled through his transformers, drawn in at higher natural pressure, and accelerated to a sharp electrical discharge. As electrical systems, Tesla apparatus cannot completely be understood or explained. One must view Teslian technology as an ether gas technology, one capable of being explained only through gas dynamic analogies. It was now easy to understand how such projected rays, ether gas streams under high pressure, could penetrate metals and insulators alike. These powerful rays often could penetrate certain materials with inexplicable efficiency. Electricity did not perform these wonders. Tesla also now understood why these discharge streams produced their smoothly hissing sounds, visibly appearing like gas jets under high pressure, ether gas under pressure. Tesla was completely mystified. He had successfully released the mystery current, normally suppressed and bound in electronic charge carriers. Unidirectional, impulsive discharges of high voltage and abrupt durations released them. What other potentials would ether gas technology release? The original cylindrical coils were quickly replaced with cone-shaped coils. With these bizarre geometries, Tesla was able to focus the gas dynamic component, which now rose up like a jet of hissing white light from the coil tip. Tesla recognized that these discharges, white, spectacular, and awe-inspiring, actually represented lost power. A power broadcast station had to evenly disperse the energetic radiance in all directions. Flame-like discharges caused the available power to undulate in space. This would produce unpredictable power drops at long distances. Consumers would not receive a reliable and consistent stream of energy. If his power transformer was to operate with highest broadcast efficiency, these flame-like discharges necessarily had to be suppressed. But suppressing these excessive ether jets proved problematic. Tesla found that the white flimmering streams were absorbed in large capacity volumes, masses in which the streams were absorbed, filtered, and expelled. The use of copper spheres atop his transformers forced the streams sufficiently apart to suppress the white flame. Power was now evenly dispersed throughout space as required. But a new problem appeared. The copper spheres, being impacted by the high voltage streams, which were composed now of where the forces were now conduct, expelled electronic components. These appeared along with the radiance, producing truly dangerous conditions. The problem was stimulated by conduction, a case where the spherical copper ball was impacted by ether throughout its volume. The white flimmering streams permeated the copper and expelled electrons. These contaminants concentrated their escape from the system as harmful blue stinging dartlets. By comparison, the white flame discharge was smooth and harmless glow. Comparing the two species, Tesla recognized the difference in charge carriers. Tesla was once nearly killed when one such dartlet jumped 3 feet through the air and struck him directly over the heart. The copper spheres had to be removed and replaced by another dispersion component. Metals were apparently of no utility in this case, being natural reservoirs of electrons. Tesla eventually suggested that metals manufactured electrons when impacted with these special flame-white currents, the carriers in the white flames becoming concentrated within the metallic lattice. He had already observed how the very air near the transformers could be rendered strangely self-luminous. This was a light like no high-frequency coil ever could produce, a corona of white brilliance which expanded to ever larger diameters. The light from Tesla transformers continually expands. Tesla described the glowing column of light which surrounds any elevated line which is connected to one of his transformers. Unlike common high-frequency alternations, Tesla radiant energy effects grow in time. Tesla recognized the reason for this temporal growth process. There were no reversals in the source discharges. Therefore, the radiant energy would never remove the work performed on any space or material so exposed. As with the unidirectional impulse discharges, the radiant electric effects were additive and accumulative. In this respect, Tesla observed energy magnifications which seemed totally anomalous to ordinary engineering convention. It was easy to control the brilliance of a room by controlling the voltage in his transformers. The light from this sort of illumination was curiously bright to human perception, but nearly impossible to photograph on film. Tesla found it necessary to make long time exposures of his discharges before the faintest sort of streamers could be made visible. This strange inability to register photographically was contrasted against the brilliance perceived in the eyes, one which required delicate control. Tesla also designed, built, and utilized large globe lamps, which required only a single external plate for receiving the radiant energies. However distantly placed from the radiant source, these lamps became brilliantly illuminated. Theirs was a brilliance approaching that of an arc lamp and exceeding any of the conventional Edison filament lamps by several factors. It was also easy for Tesla to control the heat of any space. By controlling both the voltage and impulse duration of energy in his transformers, Tesla could heat up a room. Cool breezes could also be arranged by appropriately setting the impulse duration. The key to producing all etheric action was to secure a means for actually affecting etheric deviations, the very thing now possessed by Tesla alone. Sir Oliver Lodge stated that the only means for getting at the ether was an electrical means, but not one member of the Royal Society of London had been able to achieve this feat, with the rare exception of Sir William Crookes. The Tesla method used ether to modify ether. The secret was separating the contaminants from the etheric current at the very source of generation, a feat which he had achieved in his transformers and magnetic arc disruptors. Tesla used the violence of magnetically disrupted arc discharges to chaoticize electronic and etheric carriers in metallic conductors, breaking the agglomerations which bind them together. Each component was free to separate. This condition could not be achieved in arc discharges where currents were allowed to alternate. In such apparatus, the electronic carriers overwhelmed the release of ether, and while ether was present in the discharge, could never be separated from the composite current. The extraordinary efficiency of the magnetic arc disruptor in developing etheric currents derived from several principles. Tesla saw that electrical current was really a complex combination of ether and electrons. When electricity was applied to the disruptor, a primary fractioning process took place. Electrons were forcibly expelled from the gap by the strong magnetic influence. The ether streams, neutral in charge, remained flowing through the circuit. The magnetic disruptor was his primary means for fractionating the electrons from the ether particles. Ether particles were extremely mobile, virtually massless when compared with electrons, and could therefore pass through matter with very little effort. Electrons could not keep up with either the velocity or the permeability of etheric particles. According to this view, ether particles were infinitesimals, very much smaller than electrons themselves. The etheric carriers contained momentum. Their extreme velocity matched their nearly massless nature, the product of both becoming a sizable quantity. They moved with superluminal velocity, a result of their incompressible and massless nature. Whenever a directed radiant matter impulse begins from some point in space, an incompressible movement occurs instantaneously through space to all points along that path. Such movement occurs as a solid ray an action defying modern considerations of signal retardations in space. Incompressible ray lines can move through any distance simultaneously, instantly. Should the path be 300,000 kilometers long, the impulse at the source end will reach that point as quickly as at all other points. This is superluminal velocity, instantaneous propagation. Radiant matter behaved incompressibly. In effect, this stream of radiant matter, virtually massless and hydrodynamically incompressible, was a pure energy, radiant energy. Here was a distinct phenomenon, one which did not in fact manifest with other than impulse applications. Tesla alternately called these pure etheric expulsions radiant matter and radiant energy. Neutral in charge and infinitesimal in both mass and cross-section, radiant energy was unlike any light seen since his work was concluded. Asked if radiant energy can be compared with any existing physical item today, one would have to decline. We cannot draw parallels between radiant energy and the light energies which science has long been preoccupied. But if light-like at all, radiant energy is possessed of qualities unlike any light which we have learned to generate. And this is precisely the problem. Tesla technology is impulse technology. Without the disruptive, unidirectional impulse, there are no radiant energy effects. Generating this radiant energy requires special energetic applications of succinct and brief impulses. These impulses must be generated through the explosive agency of a disruptive discharge, just as Tesla described. This concludes that portion of the book, Secrets of Cold War Technology by Jerry Vassilatos, which I care to enter into our discussion this evening. In spite of the length of this recital, I have actually edited out a number of concurrent themes to focus strictly on the material that I thought immediately relevant to tonight's thesis. Anyone interested in advanced electrical science or even accurate scientific history should read and study this volume.
My name is Tom Brown. I'm the director of Borderland Sciences Research Foundation in California. And today we're in our top secret laboratory hidden in the vast suburban wastelands of Southern California. And we're taking a look at Tesla's longitudinal electricity. The electricity in general use today is transverse electromagnetism. And what Tesla was experimenting with in his types of experiments was called longitudinal dielectricity, a polar opposite to that. And we're doing advanced research into that type of electricity. Now we'll take a quote here from the book, Experiments with Alternate Currents of High Potential and High Frequency, which has an appendix called The Transmission of Electric Energy Without Wires. And to quote Nikola Tesla, toward the close of 1898, a systematic research carried on for a number of years with the object of perfecting a method of transmission of electrical energy through the natural medium led me to recognize three important necessities. First, to develop a transmitter of great power. Second, to perfect means for individualizing and isolating the energy transmitted. And third, to ascertain the laws of propagation of currents through the earth and atmosphere. Now, the transmission of great power was, of course, carried on by Nikola Tesla in his Colorado Springs experiments, which led to the building of the Wardenclyffe Tower, which was to transmit electrical energy around the Earth. And the second point, the means of individualizing the currents, was in his experiments with harmonic resonance circuits, such as you're going to see today in this video. And third, the laws of propagation are his one-wire and wireless power transmission, where he demonstrated longitudinal currents rather than the transverse currents, which he did not feel were all that swell for propagation of electricity. So here today we're going to see some experiments in this, and now to give you an introduction to the experiments by showing Tesla's patent and the schematic that we're using is Peter Lindemann, Director of Borderland Sciences.
Hi, I'm Peter Lindemann, Vice President of the Borderland Sciences Research Foundation. Today I'm going to explain to you the basic experimental setup, which we're going to demonstrate in a little minute. Over here we have a schematic drawing of our experimental setup. And down here, I'd like to first bring your attention to Nikola Tesla's patent number 649621, which was granted on May 15th, 1900. Basically, this describes the experimental setup which we will attempt to show you today. And I'd like to describe it for you right now. This is a transmission and receiving system for what he called his wireless power transmission. The exact name of the patent is Apparatus for Transmission of Electrical Energy. And it consists of a generator system which produces the appropriate types of currents, which goes through a two-loop primary on this device here. This is the thick, darker line around, which you can see on your television screen. Inside here is a flat spiral coil, which is connected to ground at the outside of the spiral, and on the inside of the spiral is attached to what he calls the termination, which in the case of the Colorado Springs experiment was a ball, a sphere that was high up in the air. The receiving apparatus is identical in nature, consisting of a termination, a flat spiral coil, and a connection to the ground. And the outside primary or secondary of this system is attached to the loads. So that describes the patents, the patent that Tesla was granted in 1900. Now what I'd like to do is describe for you the exact apparatus which we will be testing for you today. Our generator system consists of this much of our diagram here, which includes a medical Tesla coil circa 1920, which produces our supply of electrical induction. We also have a capacitor to create circulating currents in this, which is a 0.001 microfarad, 15,000 volt capacitor built by the Faraday Corporation. And we have two hydrogen spark gap tubes, 1B22 here. And this creates a negative resistance which helps to accelerate the wave. So this is what we're using to supply the appropriate currents to our primary of our coil here, which is a two-turn flat coil made out of sheet copper. This showing the two turns, just like the two turns shown in the diagram here. Our secondary is made up of, our termination in this case is a neon bulb, which acts as a plasma, which in these low power systems works better than a large sphere. That's connected to our flat spiral. In this case, our flat spiral is made out of Teflon-coated silvered coaxial cable, of which we're just using the outside shielding, the silvered shielding, and not the inner wire, because these currents operate primarily using what's called the skin effect. And then our output, which is at the outside of the flat spiral, our output here. And now we will run a number of experiments attaching various things to our output here, showing various behaviors. Our second apparatus is identical. It has an input at the outside of the flat spiral made out of silver coaxial with Teflon coating on it, and going up to a second termination, and a second series resonant harmonic resonance circuit, which is tuned exactly the way our transmitter is, with 2 turns of flat copper sheet and connected to a second 0.001 microfarad capacitor identical to this one. And so these 2 primary circuits, one of which is energized, the other of which operates in harmonic resonance, makes up our circuit. We will attach loads to this output, as well as putting various devices in here for the transmission of our electric currents. So this is our test setup. And now I'd like to introduce Eric Dollard, who will first show us the actual physical setup of our test apparatus today, and then we will run the experiments. Eric?
Hi, my name's Eric Dollard, and I'll be running the experimental setup for the Tesla wireless transmission system. We'll go through our diagram here on the board, which Peter showed a little earlier, but now we'll show you the actual devices. For a supply of electrical induction, we have an old Fisher Medical Tesla coil from roughly around 1920 to 1930, which in itself is a complete little wireless transmitter, but we're just going to use it to charge up our high voltage capacitor shown here on the diagram, which is an old mica capacitor from shortwave radio transmitters used also around the 20s. We use these kind of capacitors because they have a very low inductance and very low hysteresis losses, and can deliver really strong high power impulses. And here's our 1B22 hydrogen fibertron tubes that we're using as spark gaps. You can use a number of other things for spark gaps, such as quenched gaps or rotating commutators with these tubes. Work pretty good for this, and they don't put out a lot of light or noise, and the negative resistance of the hydrogen plasma increases the rate at which the discharge occurs and produces stronger transients. Our primary coil is 2 turns of copper right here on the large transmitter unit. Let's hold this up a little bit. You might be able to see actual strips of copper on the primary, and then our secondary resonant coil. And of course our coil is shown here on the diagram. I might want to point out that this coil is not just a simple inductance coil, nor is this thing just a simple transformer. The inner turning capacitance plays a very important part in this coil to give it a very strong resonant frequency. And the resonant frequency of our primary oscillating circuit here is chosen to fall on one of the fundamental harmonics of resonance of this complex network of mutual inductions and capacities which the spiral makes up. And we'll go through a frequency sweep and what have you later to determine exactly what these are. Our termination is an argon bulb here at the top. And our output terminal on the outside of the spiral comes down here to a little banana plug, which we can plug various things into. This coil here serves as a loading coil to help couple the energy out into the rest of the system, increase the efficiency. So this basically would simulate maybe the impedance of the earth or the transmission medium in general to give the coil something to work into. Okay, to start off with, our transmission path is a simple plasma column, and then we have our conjugate receiving coil, which has exactly all the same characteristics except it's wound in the opposite direction. And it finally ends up with its final tuning capacitor. The same tuning circuit as the primary, so naturally we're going to get flow between the two because of their resonance, and then we have the end result, which is a 15-watt light bulb, which will be our resistance load. We'll connect across the output here. And we'll have Tom turn the switch on, and we'll see it go. So, of course, the load is lit, and we have a single wire path going from the receiving transformer through the plasma column, to the loading coil, and off to the transmitter coil. Hence the single wire method of electrical transmission. Okay, we'll take a brief pause here and we'll get into our experimental setups. Okay, our first experiment is we'll run the light bulb conventionally in the electromagnetic fashion where the circuit is a closed loop or a true circuit. And then what we're going to do is we're going to pull the plug and see if the light bulb still lights up. And we'll start off with the conventional circuit method, energize it, and of course the bulb lights up. Now what we're going to do is we're going to pull the plug on the bulb. We find the light bulb still lights up, so we're starting to get a rather novel thing going on here. You can see the wires become quite energized. High voltages on it. The neon bulb readily indicates there's quite a bit of charge. Okay, turn off the power. Now what we're going to do, let's go back to our diagram here. What we did in disconnecting the plug is we switched to this configuration here where there's no connection on the other end of the light bulb. Okay, now what we're going to do is hook an amp meter up to ground. We have a Weston, or Simpson in this case, thermo amp meter, which is not very susceptible to spurious readings because it takes actual heating to produce a result. And we're going to plug this into the output end of the coil and see how much current this system delivers to the ground. Reference to our drawings over here, this is now our setup. And if we energize the system, find that we have roughly 0.68 amperes of current flowing out of one terminal in the ground. Hence the Tesla wireless transmitter. Turn off the power. Okay, and after a brief pause, we're going to go through our experiments where we hook various devices in between the two coils and see how they propagate these currents. Okay, now we have our two coils set up with our series path, our terminals. In this case, our terminals will be here on the workbench. Terminal from the transmitting end through the loading coil, and the terminal the receiving end, and of course we can connect various items in between. And at the receiving end we have a pickup thermomilliamp meter to measure the amount of induction the device is receiving, and that'll be our determination of how effective each of our three items are here for the transmission of currents from the transmitter to the receiver.
So can you just describe this situation here? What do you got? You've got two turns of
14-gauge wire and a little magnetic pickup coil that determine how strong the field is around the coil. And of course that gives us an indication of how effective each of the items is in conveying the current from the transmitter to the receiver.
All right, great.
Okay, we'll start off with just a regular wire connection and go into the power supply, and that will give us the reading on the milliamp meter, which is, can you read it, Peter?
About half scale. Looks like 72 milliamps.
72 radio frequency milliamps. Okay, we'll turn the power off. The next thing we'll put in is a plasma column. And we'll energize the power. And the meter will read again.
Slightly less. About 65, 66.
Okay. The next thing we'll insert in is a series parallel bank of incandescent bulbs.
Now it's a lot lower, about 50 milliamperes.
Okay, so we can see now we have a definite difference between transmission through a plasma column and transmission through what would represent an effective length of conventional transmission line, in other words, wire with resistance. Plasma column tends not to have any resistance, where the conventional transmission medium tends to exhibit resistance. And of course, in direct connection, all these factors are so small that they don't really appear. Now, what we're going to do is we're going to get into some of the effects of the illumination that comes off of these incandescent bulbs, which contain vacuum, when run off of these currents. And we're going to do a comparison between a bulb running off of 60 cycles and a bulb running off of high frequency right next to each other. And this will lead us into our second Tesla patent, which is the transmission of electricity by radiant means. And we're going to show how DC can flow through space with only one wire. So we'll take a brief break here and set up our new experimental apparatus. Okay, here we have two conventional light bulbs. And they're 15 watt, 120 volt. We'll bring one up close to the camera here so the construction of the bulb can be seen.
It's too close. Yeah. Just back there is fine. And I'm gonna sharp focus on this. You have to go farther away even. They're about there. That's fine. Yeah, so you can see the filament. It's a little ring filament. That's great.
Right, and one interesting feature of these bulbs is they have a very big vacuum space, which is not usually found in most light bulbs, and they're not filled with gas like most light bulbs are. These are vacuum light bulbs. So we'll have two of them here. This one and this one. One will run off of conventional 60 cycle alternating current, and the other one will run off of the longitudinal current. And we can see the brightness is pretty close to the same. Now let Tom come over and see if he experiences any difference between the light and the two bulbs.
Okay, well, one thing I do notice just visually, and we really can't record this because we don't have the proper detectors, but just the character of the light. This the electromagnetic light, transverse, looks somewhat reddish to my eye, and this looks somewhat bluish. And it just feels kind of hot, like a regular bulb. But around this one here, I feel a pressure coming off, a charge and a pressure, which I felt a little shock there also. And but the character of the light is definitely different. There is a distinct pressure, and the higher up we turn the power going in, the stronger the pressure is. And now we'll give another demonstration which shows another characteristic of this opposite to the pressure.
Okay, one other thing I'd like to point out is the fact that this situation over here is very stable and quiet. We have, according to the Variac, 115 volts across the bulb. This light bulb here, the socket is arcing over inside, indicating there's several thousand volts across the bulb. So we can start to see some difference happening here. Now what happens is when you have gas in the bulb, as well as the filament, this very high voltage that appears across the bulb energizes the gas, and you end up with what would be a full spectrum light bulb, which still retains its incandescent characteristics. But these bulbs being vacuum, we can't really fully demonstrate this. Now what we're going to do next is we have a force coming off the bulb, then we can study this force. And what we'll do is turn the power off for a second here. And we have a little piece of copper strip dangling from insulated tape. Let me just center this up here a little bit. I can help.
No, it's got to be lower.
Why not? Okay, first we'll bring the strip near the Tesla current bulb. Turn it on. See the traction.
Okay, let me turn it off on a couple times.
Move it slightly farther away, and let me get a real tight focus on
Turn the
this.
power on. I'll bring it near it. We'll see where it pulls in. You see once now. Hang it on there. Okay, now what we'll do next. Just stop.
So that's just a piece. That's a piece of copper foil.
Copper foil, copper tape.
Hanging on a piece of
Masking tape.
masking tape.
Turn on the conventional, and of course you see we get no effect.
Even closer, right?
Right up to it, and as can be expected, there's really not much of anything happening there.
Right, okay.
Just a little bit of residual charge that was left on the metal. We'll go back to this one. And the attraction. Okay, we'll turn the power off. Now we can say, well, it's just high voltage. But what we'll do, we'll put this point here.
So now once you're bypassing the light bulb,
Bypassing the light bulb.
so we're just running the current past
just
the
going to
strip.
have the high voltage itself next to the thing.
Okay.
Turn it on. No attraction. So as we can see, there's definitely charge there. Bring the point right up to it. No desire at all to be attracted to it.
So what you're saying is that the attraction is related to the action that's happening in the bulb.
Right. The bulb is producing rays. As well as light rays, it's producing another form of ray which exhibits mechanical action at a distance. The human body experiences it as pushing out, but material objects experience it as pushing in.
Okay. Can we see that effect one more time? Let me start with it just a little bit farther away. We can turn this just so the camera can have an idea. And let me just focus right tight in there. Okay.
Ready?
Pulls it right in.
Here it goes. Okay, now what this does is bring us to a whole new area of Tesla's wireless power transmission, which we'll get into part 2. And we'll go back to the original patent and start out from there. So we'll take a brief break here.
Okay, here we're looking at Nikola Tesla's patent number 685957, apparatus for the utilization of radiant energy. Now, what Tesla was very interested in was the propagation of light and currents, beams of light and current through space, and also on how to receive these, both send and receive. And here we see the apparatus for receiving, which is basically a small condenser, one end to ground, the other end up into space, and you could pick up various cosmic radiation, such as solar. And Tesla also claimed that some of these radiations from outer space moved at 50 times the velocity of light, although there's no exact verification of that. And here we see an apparatus, a carbon arc, charging this. And down at the bottom here we see a light bulb, single wire bulb, energizing the apparatus. And what we're going to do now is show you this experiment, charge a capacitor from a bulb, and show you the discharge from it.
Okay, what we have here is a capacitor, a television doorknob capacitor, 500 microfarads at 20,000 volts. And it's connected to ground, sink. In the other terminal of this capacitor, we're going to bring near this light bulb and see if we can charge the capacitor up like Tesla did with the radiations or forces emanating from the light bulb. So we'll energize the circuit. And we'll hold the other pole of the capacitor some distance away from the bulb. Okay, let's see if we get a charge on it. We have a small neon bulb here. Capacitor seems to want to go away. I don't know if we caught
A
it.
small
Yeah,
flash.
just a small flash on the neon bulb.
Let's do it once more.
So let's start by shorting the capacitor completely to handle the doubters that we don't start with a charged capacitor. Okay, so that's completely shorted to ground, both ends, so that you can believe that this is an absolutely dead short. It's an uncharged capacitor.
Prevent it from rolling away. Okay, let's try it again.
This time let's leave it near there to try and build up a bigger charge.
Yeah, I haven't determined exactly what part of the bulb is out the best charge yet.
And bring it down by the side so it's closer to the
The
cylinder.
sides is where I feel the greatest pressure.
Yeah.
Okay, I think that'll do it.
Okay, and we'll try and keep the neon bulb in our view here, so if it flashes at all.
Little
Very
tiny
small
flash.
flash that time. Let's try it one more time. Okay, let's try it again. One time I got a very large snap out of it. Yeah,
There we go.
Pop.
Okay.
Okay, so what it wants is to be held one more spot, or one particular spot, not moved around. So it indicates the charge is different in different directions. Okay. Now what we should do is bring it near the wire, or one of the hot points around here, and make sure it's not just the electricity itself that's charging it up. Corona there, saying the currents are flowing to the capacitor. Very small flash. Let's try it one more time. Corona is going to cause a certain amount of rectification because it's an electrical conductor, so we will expect a small charge to exist on the capacitor. Now we'll go back to the light bulb. Okay. Snap. Definite difference. Okay, one other experiment we'll do is we'll bring it near the very high voltage of the neon or argon lamp. And there'll be some residual charge, I'm sure, but no snap. And we'll go back one more time. The light bulb. Okay, now what we're going to do next, our next test setup, is we're going to attempt to demonstrate the actual transmission of DC through free space.
So basically what we've just seen here is that fairly conventional light bulbs produce radiations which are not seen when the same devices are run on ordinary 60-cycle AC electromagnetism.
Right. What's involved here is what are called impulse currents, and we usually use are alternating currents. So there's a distinct difference.
Now, how is this related to like the types of energy that runs in your body?
Well, that's a good question.
Well, one of the things I thought is that all the impulses in your nervous system are actually impulses. There's like what tells your heart to beat and everything. These are impulse currents that run in your system.
Right, they're not alternating currents, they're periodic impulses.
Right, same with nerves firing and things like that. These are all impulse currents. So this running these systems on impulses is much more like the way living things operate.
Exactly.
Well, another observation on that is that the character of the light coming off of these bulbs with the Tesla currents on them is much more akin to the type of light coming from the sun, where there's a radiant pressure outwards, and it seems to be a natural type of light, much more beneficial to the body. This type of light would probably go quite well in hospital operating rooms and schools and things like that. It's a very open-ended area of research.
Right, it could be demonstrated, even though we're not capable of doing it here right now, but it has been demonstrated before that it does take less electricity to produce light by this method, particularly when gases are in the bulb. One thing we can also show here, so if the bulb's back up in series, can you hand me the small green clip? Conventional series circuit. Going back to our original demonstration where we pulled the plugs, we'll do that again when we turn the power on. Okay, see the bulbs light up, of course they're all in the series pad. You notice one starts off a little brighter than the other. Okay, turn the thing off. Turn it on. And of course the light bulbs still light up. And We don't feel the pressure quite as strong around the cap. The intensity of the filament is not as great. It's definitely there. We'll do a quick capacitor charge off of that, and then we'll get into the next part of our experiment. Oh, there's a little bit less than sun, even though the voltage is higher. Yeah, it's much smaller, but still a spark. Okay, we're going to put our next setup together now. Okay, we have our next test setup here. We'll start with our electrostatic voltmeter, which is a unbled MOSFET input going to a bridge amplifier, which will read out on our center scale voltmeter. And that connects to our antenna here and ground, which is down here underneath. And then on this end we have a source of high voltage direct current, in this case of positive potential, and an electrostatic power supply down on the ground there, a 0 to 30 kilovolt rectified radio frequency type power supply. If we can select the polarity, we've chosen positive for this because it seems to work the best. What we're going to do, we're going to focus back on the meter. I'll get up here so I can see the meter. And then Tom is going to crank up the power supply voltage slowly and read off the voltages on the voltmeter as he goes up.
Here we're about 5 kilovolts, 7 kilovolts, 9 kilovolts, 10, 11,
The meter's starting to jump, and I can hear corona coming off the high voltage point.
We're at 15 kilovolts, 16, 18,
The hissing now is quite strong.
20,
Transmitter lead.
25. I'm up to max, which is about 28 kilovolts.
Okay, and we're not really getting much current reading other than just the displacement current of the varying potential. Okay, bring it back down.
Okay, power off.
Now we're going to attach this fluorescent lamp to the receiving terminal. And this single terminal neon tube to the transmitting terminal is our plasma columns. And then we're going to try this experiment again. Okay, the meter now responds a little better.
So start reading more.
We're at 4 kilovolts, 5, 6,
Okay, hold it right there.
about 6.5.
So this is already working.
It's already
Better than
working
3
6.5
times better.
kilovolts. Okay, bring it up a little more.
What do you got there?
I'm at 8.
Okay, and
Let
we got
me turn the sensitivity down here
the
now.
meter pegged.
Okay, let's just hold it right there for a second. So now the meter stands, even though there's no variation in potential, current propagation still exists. And we can't see any glow in these tubes either, which is rather peculiar. It's a dark
Now,
discharge.
you walking behind there made the meter swing the opposite direction. So do that again. Put your hand, okay, that doesn't change it. Oh yeah, it changes its
Motion.
Well, by motion in the electrostatic field, of course,
Right.
it's going to introduce alternating currents.
Now it just swung over to the opposite side,
And it's holding.
and it's holding. So back away again. Yeah.
Switched over, your feet by the ground.
Oh yes, I'm charged up being insulated.
Yeah,
What's happening?
there you go. So it's still propagating a continuous current.
Right.
So this demonstrates what? The wireless.
This represents what Tesla was thinking about transmitting DC through space.
DC through space.
Right, and using the appropriate asymmetrical impulse currents at the transmitter end and synchronous converter at the receiver end, one can get very effective transmission through space of DC, which we indicated already existed close to the light bulb at the television doorknob capacitor.
Okay, so you want to turn that off, Tom?
Turn that off. Put this thing back on 0. I had to rebalance it. in order to get the scale. I want to crank it up again one more time just to see it do it again.
Okay. Quick reaction there.
There it is.
It's come to about 7.5 there. 7.5 kilovolts. Up to 10.
10's the meter.
Okay. They're down to about 4 there. Down to 0.
Okay, well that concludes our experimental demonstration current transmission. What we'll do next is give the dimensions of the apparatus and a practical application of one of the coils operating a shortwave radio receiver with no antenna tower.
So this pretty much vindicates Tesla's patents. A lot of people have taken a look at these patents and thought that this was all fairly novel and interesting, but I've never seen anybody duplicate these experiments before. Have you? Besides right here in this laboratory?
No, because no one is really building the apparatus the way Tesla intended, and also everyone tries to explain it away with conventional laws of physics.
Mm-hmm. So what would be a conventional way of explaining this away?
Well, it would be that ions are being carried from here to here, but we saw even when we had a heavy corona on the point, we didn't get a continuous current reading on the meter. Okay, now we found earlier, and we were not able to duplicate it this time, probably due to the severe humidity in the room, that even with no tube hooked up, you will reach a certain threshold where the meter will read.
Mm-hmm.
And Tesla pointed out that when you exceed a potential gradient of 12 million volts per centimeter, okay, in this case it's kilovolts per millimeter of curvature to get the same quantity,
Mm-hmm.
that current would flow through space and propagate outwards, building up a conductive media behind it. And he had figured this way he could tunnel a path between the transmitter and receiver to carry direct current or impulse currents.
Mm-hmm. But not alternating currents.
Not alternating currents. He didn't plan to do it with alternating currents. It'd be impulse currents. Most of his work was with impulse and oscillating currents. The limiting case of an oscillating current with no dampening being an alternating current, and the limiting case of an impulse current with no decay factor to it or rise or fall would be a direct current. So impulse currents and oscillating currents are what Tesla was working with, and what we utilize are direct currents and alternating currents. So there's a distinct difference, all 4 of those being the general number of, the 4 currents, general currents of existence.
So what you're saying is that the general way of explaining this away is fairly well shot when we connect it to the plasma tube there, and it works much better.
Right, and the plasma tube remains dark.
Exactly.
And the plasma tube on the receiving end obviously cannot be glowing.
Correct, but that makes the receiving end receive better.
Receive better. And there seems to be, we take the plasma tube off of the receiver, still energized here.
Yeah, it can come back up.
And it'll come back up. We'll probably still get a reading to some extent. Let's just make sure.
Okay, with 5 there. 10.
So you're all the way up to 15 kilovolts.
And the receiving is much lousier.
Oh, now you've reached the threshold point and I can hear the corona.
Yeah.
It's getting a little transmission. Keep on going
I'm
up.
at 28. I'm up all the way.
Okay. Now most of that will be the radio frequency of the corona producing displacement currents in space, which is not direct current anymore.
So yeah, there's a threshold that came down about 25. It just dropped.
So we leave this to the audience to explain. I mean, those that want to explain it away will be fine and dandy. You're not going to get too far in Tesla's work trying to explain everything away and saying he was wrong. But if you develop the attitude that Tesla was right and try to systematically duplicate his experiments, as you can see with relatively simple stuff such as fluorescent lamps and old insulators and junk meters, that it's quite possible to duplicate his experiments. And none of these things are tuned to each other either, and the little fine details worked out. We're already getting results here with the very basic beginnings. No lamps or tubes specially made, coils not harmonically balanced so that all the odd order harmonics add up in the proper phase relationship. None of these things have been dealt with yet because we just don't have the money, time, material, manpower, etc. to do this. But just the basic duplications and copying of the patents already indicates to us a good start.
Okay. For those of you who are interested in duplicating any of this research, I'd like to describe for you the construction of the coils that we've been testing. Over here, we have one of the Tesla coil apparatus built by Eric Dollard, facing up. And I'd like to just describe for you its actual construction. Here, we have the primary, which consists of 2 turns, consisting of 3 layers of 1 inch wide by 10/1000ths of an inch thick bronze strap. So that each turn is made up of 3 straps of that dimension. The secondary, which begins here, or at the output, and ends here at the termination, consists of 20 turns to here, and then another half turn around here of Teflon-coated silvered coaxial cable, which is approximately 85/1000ths of an inch in diameter. The outside dimension of this secondary coil is approximately 18 inches, and the inside diameter is approximately 13.5 inches. Each turn begins here and goes all the way around on the bottom, and then comes to the top of the same layer, and then goes all the way around again, and then comes to the next inside. So the first 2 turns are here, second 2 turns are here, third 2, fourth 2, fifth 2, etc. So that each adjacent winding has, you can zoom in on this section right here, Tom. The first winding goes all the way around in the outer slot here, and then the second winding is right on top of it, so that these 2 windings are very close to each other. Then when it comes around to here again, that moves to the next inside dimension, and 2 turns are wound there, and then 2 turns here, 2 turns here that are on top of each other, so that there are 2 turns that are very close to each other, and then slightly farther away. This creates these relationships of mutual capacitance and induction, which Eric was talking about earlier. And the coil basically comes to a 20th turn ending here, and then a single turn comes out through here and goes to the termination, which in this case is an argon bulb. Primary is attached with many single strands to our 0.001 microfarad capacitor. In this case, we're using a smaller one because we're about to take this unit as our receiving unit out into the field to see how far our other transmitter unit can transmit. So this is the construction of both of these coils. The other coil has these primaries and secondaries wound in the opposite direction, so that these are complements of each other. So now you know enough to build one yourself.
One thing that should be pointed out is the total volume of copper used in the secondary should equal the total volume of copper used in the primary.
Okay, but in this case we've got bronze here and silvered.
Yeah,
so
it's
in other
a
words,
little bit
metals.
different.
Yeah.
So what you have to do is you have to compensate for the skin effect to figure how much is used. And basically, frequencies of these type of coils, it's not good to use conductors with a thickness much greater than 10 mils. Otherwise, you have to readjust your volume.
Mm-hmm.
The Tesla found that when the copper weights or conductor weights are equal in the primary and secondary, that you got the best effects. And then weight could be best expressed rather than weighted volume in this case, and then with the skin effect, it finally resolves to equal surface areas.
The surface area of the primary equals to the surface area, the effective surface area.
Yeah, that's what eventually you would strive for, but it's the simplest way to do it is by volume.
Mm-hmm.
And these are designed on a per volume basis, equal primary and secondary volume of copper. The reason that all the little wires are used to connect to the capacitor is to eliminate the skin effect and reduce the stray inductance in that area.
So that the magnetism stays
inside the
coil.
enclosed loop around.
Could you hold that up so we can show how it's connected onto the capacitor? It's not real clear.
Maybe tilt the thing up, maybe? Yeah.
Okay. Focus in
So
here.
even though the currents and voltages might be small in the receiving coil, you still have to use high voltage and high current apparatus to keep the resonant frequency sharp. It's very important that the effective resistance of all this be kept very low. That's the reason for using sheet copper or multiple strands of smaller conductors. You might want to tilt the thing up sideways and show how the yardsticks were notched and the insulating loop that holds it up to give the experimenter an idea on good mechanical construction.
Okay, get a pretty good shot of the notches there.
These were carefully run through a table saw that had the blade at the specific depth, over and over and over and over and over and over and over to create each notch.
Yes, I spent many hours doing it.
Yes, exactly. So this is what the experimenter has to do. This is the boring side of science.
And then the outside loop is made of phenolic type insulating material. It was cut out of a large drum. And that basically holds the whole thing together. And of course the object is supported in the air by the ceramic post insulators, which could be wood or any other so-called non-conducting medium.
So-called.
Now, of course, if you want to use these things for very high voltage and high power, then you have to get rid of the wood and use all glass epoxy where the yardsticks are. Eventually, the thing works best if you use all Teflon and silver. Those are basically the two materials to use in the construction of all this, is Teflon and silver.
Yeah, because Teflon doesn't break down.
Right, and it does punch through, it won't crack or melt. And the silver doesn't corrode and offers the best reflectivity, but then of course the skin effect is going to have to be compensated for, and the silver strands that have to be thinner. That's one of the reasons for using the Teflon insulated coax, because they can't put the Teflon on the wire until they silver it because of the corrosive gases that are formed. So it makes it perfect for this. And of course, because of the skin effect, there's no need to have any metal on the inside, so the inside wire of the coax is never used.
If anybody wants to duplicate these experiments and has any questions, just write to Borderland Sciences Research Foundation.
Okay, I'll describe our test setup here for our wireless transmitter. What we're going to attempt to do, and for the first time, we haven't tried this before, is we're going to transmit a shortwave signal with this Tesla wireless transmitter, and then we're going to go down to the beach with the receiving coil and connect the screen to the salt water and see if we can pick it up. So I'll describe our setup here. This is similar to what we did before with the spark gap, but now we're using a CW oscillator. So what we have here is an oscillator to produce shortwave signals. Right now the oscillator is 2955 megacycles, 2.955 megacycles. And the oscillator connects to a push-pull cathode follower, which delivers a push-pull output that we're connecting across our primary arrangement, this being our main capacitor here. Okay, we have an RF milliamp meter here, 0 to 100 milliamps, with a shunt across it to multiply it by 2. And that connects to the neutral lead of the coil, which is right here. You might want to zoom in on that so we can see that the coil actually comes off there. The capacitor out of the way here.
Okay.
You see the final turn or the beginning turn, depending on how you look at it. The coil comes around, connects to the neutral lead. The other end of the coil, in the middle here, comes up and connects to the neon bulb. You see the neon bulb is lit. Even though the video seems to make it look like it's lit all the time. So what we'll do is we're going to sweep through. Okay, let me point out that the meter again is connected to the sink. You might want to sweep over and show that it's grounded to the sink.
Okay, there's a sink.
Get the lead up so we can see. It's actually connected.
You now know that it's connected to the sink.
Now ideally the coil should be very close to the ground and connected to a zero inductance grounding system, in other words a plane. But we have to use this lead for now on the bench here, so that introduces some stray inductance and throws the frequency off. Okay, now we're going to sweep through here. We'll start with 1.6 megacycles. And we'll go up. And the meter starts to rise. 1.875 megacycles is one resonant frequency. Call this resonant frequency A. And keep on going up. The meter rises very sharply on this one to back to the 2.945. It's resonant frequency B. Now, one of these resonant frequencies will be a predominantly transverse wave, and the other resonant frequency B, will be a predominantly longitudinal wave. Any coil, any radio receiver or radio transmitter will have these two components. And as we'll show later, a radio receiver can either be used to receive through the ground or receive through the air antenna, elevated antenna or aerial, depending upon which mode of its input tuner you're selecting. And if the parasitic capacitances in the coil are reduced to a very small value, then only the transverse wave will predominate and the longitudinal wave will disappear. What we're using here is the capacitances in the coil to produce these effects. These double frequencies indicate that there's 4 constants involved, 2 inductance and 2 capacitance constants, giving a quadrature or 4-pole equation that will give us a pair of resonant frequencies, as we can see on this. Now, ideally, the coil should be balanced so these frequencies fall together and has only one resonant frequency, but no mathematics exists for this as of yet. And we don't know if Tesla figured this out or not. His mathematics was also very poor at the time, so he had to do it purely by empirical and experimental means. But he had the time and dollars to do it in his beginning work, and he probably achieved this, which should magnify the effect several thousand times. Okay, we're going to show our shortwave radio here. We have a small Army unit. 2 to...
If you tilt it up and get a little light on it.
2 to 12 megacycle receiver. Runs off the batteries.
Focus in here.
So we have no ground connection or 60-cycle noise problem to worry about. We can take this around, the battery packs in here. It's a vacuum tube receiver. And this is, we have the leads brought up that connect to our antenna input transformer, which will connect to the receiving coil. Now what we can do right now, the receiving coil's right here. Let's hook it up for calibration purposes. So you can hear our transmitter on location here and spot our frequency. So I'm going to put the receiver across the capacitor. Take our neutral terminal and just bring it out a little bit for now to set up impedance reduction at that terminal. Plug in the loudspeaker. And we're reading on 2.994 roughly. Hard to see on the dial. It's not a very finely calibrated receiver. Okay, and I'll lock the dial. Then we'll take the thing down to the beach and we'll see what we can pick up. Okay, what we're starting with here is we have a copper screen sitting in the salt water.
Okay.
Lead comes up, connects to the neutral lead of the coil.
Right.
We have a shortwave receiver hooked up to the capacitor directly.
Basically the same setup as a lab bench, but instead of the sink, we're now hooked to the ocean.
Okay, and the laboratory is about 3,000 feet that way, behind these rocks.
Okay.
Now, can we hear the tone?
Yes.
Sure? Let's get right up to it so you can hear it.
Without a doubt.
Okay, let's go up to the receiver so we can see the frequency dial. Okay, we're in there. Okay, and to show that the coil's working, disconnect the lead and the signal drops way down.
Okay, let me back off here and get a full shot while you do this. Okay.
So I think that pretty much demonstrates what's going on here. So we'll go back to the laboratory and wrap up with the conclusion.
Well, that concludes today's practical demonstrations into Tesla's longitudinal currents. As you can see, this type of experimentation is quite easy to do. All you have to do is go back and see what Tesla said and reproduce the experiments, and you'd be amazed at the results. And which that raises a big question with all the work going on in Tesla these days. Why isn't its work being spread more? As you can see from the scenery around that we've been doing, we're basically working out of a garage here and producing equipment by hand out of the scrap yards. But that just shows that anyone can pretty much do this equipment if they have a basic engineering background and can put equipment together. But all in all, in summing up, we can say that there are very novel things that can be done by experimenting with Tesla's electricity. And this video shows that we pretty much discovered a lot of it as we went along. This wasn't prepared, we just sort of winged it and wanted to show a day in our lab with the experiments that have been going on. In the future, we will have much more coherent and practical demonstrations for people to carry on with. So I'd like to thank you all for watching, and we will be back from our top secret laboratory again sometime in the near future. Have a good day.